All right, I'm going to show you the second problem of separation of variables. This is what makes these a little different. It's just got one letter over here, and this bugs people a little bit. It's just got an H. We're doing DHDT, and some people are like, well, where's the T? It's okay. When you separate, the H has to go with the H, and then over there with the T, there won't be any T's to put with it, but you can always just leave constants over there. Like, for example, I would leave this negative 1/4 here and send the H minus 27 over there. Okay, we'll do that eventually when they ask us to. So they said that this is a baked potato. At time 0, the internal temperature is 91 degrees. So it was boiled, and now it's sitting down. The temperature's gonna, we have a decreasing. Obviously it's cooling off. It's got a negative there. And so we have to, first off, for part A, write an equation with tangent line at 0. Well, you guys are so used to writing tangent lines with x's and y's, which is fine, but which letter is x, which one's y? Well, usually our formula is dy dx. That might help you. So h is the y and t is the x. I wrote that over here. And so when I write an equation, it's h minus the h value, which is 91, because there's our point that works, slope, and then t minus 0. So there's your equation. Now, how do I find slope? Remember, we plug into the derivative. So I got to plug into dAct this point 0.91. So I'm going to plug in 0. Now, there is no t value here, so I can't plug in the 0, but I do plug in the 91. 91 minus 27, we got 64. Negative 1/4 of that is negative 16. So that's your rate. So I plug it in here, and there's your tangent line. Now, why do they usually have us write a tangent line? Because there's some curve, maybe it's like this, and we're going to use the tangent line to predict what's going to happen down here. We don't have an equation to do it, so we use the tangent line to predict other values. So they asked me to, find the internal temperature after 3 minutes. So you could tell them you're going to plug in 3 at t equals 3. All right, that's a negative 48 over there. Add the 91 in. What is that, 43 degrees? So after 3 minutes, the temperature's down to 43 degrees Celsius. To you guys, that'd be cold, but that's nice and still warm. So 43 degrees Celsius is the temperature. So that's what's happened over time. All right, part B, this one stumps some people, is take a second derivative and then they ask a question about it, and I'll explain the question. So let me erase this. So let's take our second derivative for part B. So you got to take a derivative of the first derivative. Some people freak out with that also, but this is just like taking a derivative of an x. But remember, we're taking derivative with respect to time, and this is not a time. So remember, we're like related rates. If I take a derivative of x, it's 1. But if I take a derivative of x in terms of t, it's dx dt. So this is, if I distribute the negative 1/4, I have negative 1/4 h plus 27/4. Well, 27/4 is just a constant. So when I take the derivative, he's going to be gone. So the front is negative 1/4 h. So the derivative of negative 1/4 is negative 1/4. But to take a derivative of h is dh dt. So it's negative 1/4 dh dt. Well, dh dt is the original problem. So, which is weird. You're going to plug the original problem back in. So it's negative 1/4 dHdt and negative 1/4 times dHdt. So I actually get positive 1/16 h minus 27. And that's my second derivative. Now, when we're trying to find this temperature around 91, this is going to be now a positive value. Now remember what the second derivative does is gives me the concavity of the graph. So what they asked me was to determine whether your part A is an underestimate or overestimate to the graph. So remember the tangent line. When I did a quick little drawing, I drew it right here. Well, our graph is actually concave up. So actually the line would have been right underneath it. So remember when the graph is concave up, because the second derivative is going to be positive at this time. You can see it's all positive here when I plug in 91 here. The tangent line is actually going to be under the graph, so it underestimates the actual value. So I'm not writing anything down right now for part B, but it says, tell me whether the answer in part A underestimates or overestimates. It definitely underestimates, and the reason is because the graph is concave up. And when the graph's concave up, tangent line is underneath, okay? So whenever they ask about a tangent line, the concavity will tell you if it's concave down, the tangent line's on top, it overestimates. It's giving me a higher value than the graph does. And when it's below, it gives me a lower value, okay? Underestimates, if you forgot all that stuff. All right, part C, it says an alternate model is given for this thing. Let's see here. For G, so they're giving us a G equation instead of this H equation, okay. We could have used this equation for answering this next question. For some reason, they wanted to switch it to a different equation. I'm fine with that. Can barely see it. Looks like 2/3. So they give us this equation for G now, okay? And it says where G is measured in degrees Celsius again, and G of 0 is 91, so it's pretty much the same problem. They just changed the problem. They give us the same information where they're saying G of 0 is also 91. Okay, so different equation for some reason. All right, find the expression for G of t. They want the original equation. So this is where the separation of variables comes in. How do you find the original? Again, there's G's but no T's. So the G's have to come over with dg. So I bring this over, and then there's just a negative sign, -1 with the dt. And that's all you do. It freaks people out because they have no t's to send, but that's okay. All right. So now we're solving this problem. So we want to find the original, and then they ask us a question about it when we get to the end. So let's go ahead and finish. If I'm going to take the integral of this, I would bring this up as -2/3 to take the integral. So the integral, you're going to add 1 to 2/3, you're going to get 1/3. Divide by 1/3, which gives you a 3 in front, and then -t plus c. Integral 1 is just t, right? All right, so there's our original, but we gotta find our c. They said, remember 091, so we can find c now. Let's go ahead and find over here. So I plug in 91 over here. 91 minus 27 is still 64. The cube root of 64 is 4 times 3 is 12, so that side's 12. And I plug it in 0 there. So we get c is 12. All right, we're getting there. All we have to do is solve for g. So it's got a few math steps that I'm going to do. Let me erase all this. I think I can fit it in over here. First thing I'm going to do is divide by 3. So when I divide by 3, I can just divide that whole side by 3. It goes into 12, but it doesn't go to t, so I can leave it below it. Then this is 1/3, which means it's the cube root. So you're going to cube both sides. Remember, do the reciprocal to the power. So 3 cube both sides. So when I cube both sides, that gets rid of the 1/3, and so I have this whole side cubed. Send the 27 over. And now you got your g of t equation. All right, so there's your original equation. You separated variables, same steps we always do. And let's see what they asked us to do with it. Find an expression. Based on this, what's the temperature at 3? So they wanted to kind of see what the actual temperature with this equation, does it compare to when you found temperature at 3 before. So we got to find g of 3. Because this is g of t. I just wrote g of t, same thing. So plug in 3. -3 plus 12 is 9, divided by 3 is 3. 3 cubed is 27. 27 plus 27 is 54 degrees. Right. Now remember when we found the approximation before, we got like 43, something like that. So you can see how, remember, it was underestimating the actual value. Okay, so that is separation of variables the other way. And they gave us a problem with B's one time, waste like this, where it looks very similar to this. The mistakes people make is when they do the second derivative. You just got to remember that, I mean, I didn't write it out for you, but this is the equation you're taking the derivative of. I mean, how simple is that? Derivative of that is -1/4 dHdt. That's it. Taking derivative with respect to t. So that's where people get stuck on this problem. And they complain about it, but not a big deal. All right.